So I wonder if we can sort of stop for a moment and take stock of the information we have so far in the course really so far. What we have so far is all of our vast reservoir of knowledge about limits, how they work, how to evaluate them, how to work with them. So we have all this limit notion under our belts. And then we also have the definition of the derivative. All right, the definition of the derivative. So if f of x is a function, then f prime of x is the derivative. This is the symbol for the derivative, and it is found by the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. If, again, if this limit exists. If this function is differentiable, then this limit exists, and then we say this is the derivative of that function. We also have the alternate version of the derivative. That's if we're talking about the derivative of a function at a particular point. But all that said, we have our information about the limits, and then we have the definition of the derivative. Now, as we have seen, excuse me, as we have seen, working with the derivative in this form can be a bit unwieldy. It can be a little bit troublesome. What we're going to now do is develop some basic rules, some basic theorems, essentially, of how to work and find the derivative of certain functions without needing to go back every time to this limit definition. And so what we're going to talk about here are the basic differentiation rules. Now, the differentiation means finding the derivative or computing the derivative. So derivative, differentiation, differential, all those words are in the same melting pot here. So we're going to start with some very simple functions and build up from there. Once we know how to find the derivatives of very, very simple functions, and we know how to combine simple functions into larger functions and find those derivatives, then we're going to build our storehouse of information about what the derivatives of the various functions are. And so we're going to start sort of at the beginning. What I will do at the start is I will go through a verification that the statements I'm making are correct. You do not need to be able to do that. I'm not going to call on you to be able to reproduce the proofs. I'm going to supply those to sort of get you in the feel for what the calculus is about. It's a step up from the work you've done up until now. We're going to actually prove and talk about proof and why that's important and how that plays out. So all that said, some of the very initial rules, I'm going to show a verification, a proof that those are actually correct. You don't need to be able to reproduce that. All you need to be able to do is apply the rules correctly. Know when which rule applies, and then apply it correctly to get the final result. And then once you have that final result, in many circumstances, we're going to be asked to do something with that result. So you need to have a much more practical understanding, how to do the actual computations, how to do the actual problems themselves. Less leaning on being able to reproduce the proofs. So I'm not going to be asking that of you, but I will be, at least in the short term, for some of the more basic ones, I will show and demonstrate that these properties actually do, in fact, work. As we go through the list, we will begin to fade away from that, and we will begin to accept some of these properties without requiring proof. I need to leave something for you when you take your advanced calculus course or your real analysis course. And so we'll kick those cans down the road for a few semesters and let you enjoy them in that setting. All right, so for now, the next piece is a little bit of notation. We want to consider constant function. Now, you're familiar with constant functions, things like, an example of a constant function is f of x equals, and you can pick any constant out of the number line. I'm going to pick f of x is equal to 4. So we know what the constant functions look like. If this is the coordinate system, if this is 4, then the graph of that function, these are the horizontal line functions, right? So the function f of x is equal to 4 is here, and we want to talk about what is the derivative of that function, all right? And so understand that when we talk about this function, let's make sure that we all sort of understand that or are familiar or refamiliarize ourselves with this. So if I just pick this function f of x is equal to 4, what do we mean by, let's say, f of, pick a number out of the sky, f of 8. What is f of 8? Well, what this function, that's what it means to be a constant function. F of 8 is 4. What if instead of 8, what if I had picked negative 10? Well, f of negative 10 is 4. What if I pick an f of w plus 9, some crazy thing? That's 4. What if I pick f of negative x squared plus 4x minus 7? That's equal to 4. What is f of x plus delta x? Gee, I wonder why I asked that question. Because that's also equal to 4. F of anything is equal to 4 for this constant function. And of course, if 3 or 4 minutes ago, instead of saying 4, if I had picked 9, then all these would have been 9. Or if I had picked f of x is equal to negative 2, then all of these would have been negative 2. The point is f of anything is negative 2. So that's one little piece of the puzzle. The next bit is this. If I write f of x is equal to 4. Now, here's preview of coming attractions. It turns out, and I will formalize this in just a few moments, but it turns out that the derivative, that if f of x is equal to 4, then the derivative, it turns out, is equal to 0. Again, don't worry about that for now. I'm going to demonstrate that in just a bit and verify this result. But this is one way to state what's happening here, that if you have this function, then this is the derivative. Eventually, we'll be doing this with other expressions. So eventually, we'll be saying if f of x is equal to x to the 4th, then f prime of x is equal to, and we'll write that here. The point I'm making here is, if you use this notation, every single one of these properties requires 2 lines to write. You need to write the original function, and then you need to write the value of the derivative. It turns out there's a more concise way to express this information. And the standard procedure, and that's what I'm going to do, the standard procedure is to use that more concise way to express this. Rather than write this statement with 2 lines, what we will do is this. We will use this notation. This says the derivative, with respect to x, the derivative of f of x is equal to. Now, in this particular case, we are going to find out in just a bit that that's equal to 0. But the nice thing is, this is a way to express this information using just 1 line. And so when we get here, what we'll do is we will write it this way. D by dx of x to the 4th is equal to, and then we'll write what it's equal to. We'll find that out here in just a little bit. The point I'm making here is I'm going to use this 1-line notation rather than this if this then that 2-line notation. So with all that under our belts, I think we're ready to start writing out some of these properties. And again, these are in no particular order, but such as it is, here they are. First property is this. This is a constant if k is a constant. The point making here is it doesn't matter if you're talking about f of x equals 4 or f of x equals 11 or f of x equals negative 15 or f of x equals 0 or f of x is equal to negative 1.47. It doesn't matter which particular constant you're discussing. All of them fall into this category. All of these are special cases of the generic expression f of x is equal to k. And so what I'm talking about here is any constant function, any constant. And so what we're saying here is the derivative of a constant is 0. The derivative of a constant is 0. The derivative of a constant is 0. Now, you got to be on your toes. Some of these properties are very similar to the limit properties that we learned. Some of them are not as similar. The limit of a constant is the constant. But the derivative of a constant is 0. Those are different. They're related, but they're not the same thing. And so you need to make sure at the very beginning you get that settled in your mind, because if you don't, you're going to be making that mistake over and over and over and over and over again. So the limit of a constant is the constant. The limit of the function f of x equals 4. The limit of 4 is 4. But the derivative of the function f of x equals 4, the derivative of 4 is equal to 0. So that's our statement. The derivative of a constant is 0. Now what I'm going to do here in the blue, is something that I'm not going to expect you to be able to do. This is, for the record, I'm going to say that this actually is correct. This is not true simply because I said so. Although I would understand that if you sort of see me as this, oh my goodness, yes. Yeah, you would certainly accept my word for it. I understand that. But the reason this is true is not simply because I said so. The reason this is true is because that's what the definition of the derivative implies. And so I'm going to show that. So you do not need to be able to reproduce this. Really, officially, you could skip over this part of the video and you'd be fine as far as the course is concerned. But as far as actually learning and gaining some understanding, I think this is an important piece of the puzzle. So the reason this is true, here's my proof. My proof is this. The derivative with respect to x of the function k is equal to, it's the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. And let me get some space here. Where f of x is equal to this constant function we're talking about. So the derivative is equal to that. But we just argued this earlier. F of anything is k. It doesn't matter what you put in here. F of anything is k. That's what it means to be a constant function. So this, because of this rule, f of anything is k. So this is k minus, and then this, well, I know what that is. That's k. F of anything is k. It's k minus k over delta x. And then when you simplify that, that's the limit, delta x goes to 0, of 0 over delta x. I'm not doing the limit, I'm just evaluating that expression for now. And so that's equal to the limit as delta x goes to 0. And that simplifies to 0. Now the question is, as we said earlier, what is the limit of a constant? The limit of a constant is the constant. In this particular case, the constant coincidentally happens to have worked out to be 0. And so the limit of the constant is the constant, and in this particular case, the constant of interest is 0. So therefore, the derivative with respect to x of k is equal to this, which 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 is equal to this. The derivative of a constant is 0. So that's the proof of this statement. You do not need to be able to reproduce that, but that's the basis, that's the proof, that's the verification that this property is not something I just pulled out of a hat. It actually does follow the rules of basic limits and the basic definition of the derivative that we've talked about before. All right, so let's keep on See if we can gain a little bit of momentum here. All right. Well, let's do this. So how would this work? If f of x is 9, what's f prime of x? 0. If f of x is negative 3.798, f of x is a constant, then the derivative is 0. If f of x is 0, it doesn't matter what the constant is. Doesn't matter what's here, doesn't matter what's here, doesn't matter what's here. I'm sorry, wrong spot. Doesn't matter what's here. The derivative is 0. The derivative of any constant is 0. All right? What's next is one that this is all over the place. You start to use this rule almost without even realizing it. And the next one is sort of like it. The next one is the power rule. This one is so important, it has a name. The power rule. And it says this: the derivative with respect to x of x to the n. And let's say if n is any, right? N is any rational number. If n is any rational number, remember rational is code word for fraction. X is raised to any power you want. I can have x raised to the 9th. I can have x raised to the 1/4. I can have x raised to the -2. I can have x raised to the 0. I can have x raised to the negative 8 1/3. I can have x raised to the positive 7/4. I can have x raised to any fraction power, positive, negative, whole number, any rational power. The derivative is given by n times x raised to the n minus 1. This is the power rule. And if you had a nickel for every time over the next 3 semesters you're going to be using the power rule, you would end up with probably, we're talking a few $100s, because this is all over the place. You'd lose count before you got your money, because this is all over the place. The power rule. This is the power rule. So what is it? If n, the exponent becomes the coefficient. This is sort of the plebeian way to look at it. The exponent becomes the coefficient, and then you subtract 1 from the exponent. So what are some specific cases of this? What would be, so let's do some specific cases here. What if I had x to the 7th? What's the derivative of x to the 7th? Well, in this case, n is 7. So this is n. The exponent comes down to multiply. 7, x to the, and then what you do, you subtract 1, 7x to the 6th. What is the derivative with respect to x of x to the 2/5? X to the 2/5. Well, what is that? That's 2/5, right? N is multiplied. X raised to the power. Now what I need to do is take 2/5, subtract 1. 2/5 minus 1, or a better way to think it, 2/5 minus 3/5. 2/5 minus 3/5. 2/5 minus, 2/5 minus 5/5. We're going to subtract 1. 2/5 minus 5/5. 2/5 minus 5/5 is negative 3/5. Right? Now, if you wish, this is the same as, you can take this negative exponent and simplify this. This is 2, the 5 is here, x to the 3/5 in denominator. So you may, if you wish, leave it this way. You may, if you wish, rewrite it this way. In this particular case, it doesn't matter to me which one of those you pick. My recommendation is just let sleeping answers lie. If you leave it here, you get full credit. If you change it, you get full credit. If you leave it here, you get full credit. If you try to change it and screw it up, now you don't get full credit. So the best thing to do is just put a box around it, leave it alone, and let it sit there. All right? And it doesn't matter what the fraction is. So the same rule would apply. What if I had x to the negative 3? Well, do the same rule. Multiply. And then I need to take negative 3 minus 1. Negative 3 minus 1. And you got to make sure you do the arithmetic correctly. That's stinking arithmetic. I'll get students. I'll get Calc 3 students. Negative 3 minus 1 is negative 2. No. Negative 3 minus 1 is negative 4. So make sure you do the arithmetic correctly. Negative 3 minus 1 is negative 4. So, power rule. Now, I'm not going to go in the mainline discussion. I'm not going to go through a proof of this. What I'll do, I think, after this video is I'll make a separate one, and I will go through a proof of this. At least I will genuflect toward a proof. I won't do all the minute details, but you'll be able to see where it comes from. For us, for now, be able to use the power rule in any circumstance. All right? So we have the derivative of a constant, and we have the power rule. And those are probably the two basic bedrock rules. Now, what we're going to do is take those and build with them to do other work. And that's going to be on about when we get to the next collection of videos. So make sure you have no doubt the derivative of a constant is 0, and the derivative of x to the n, power rule, this is n times x to the n minus 1.